Hello, KNES 415. Hope everybody's safe out there. I'm not going to lecture on any new stuff, but I will try to clarify some of the stuff that we're doing. Remember, I'm just trying to give you the so what in terms of applying some basic biomechanical things to our everyday life and work towards how muscles influence motion through the context of contraction. So we talk about work, power, and energy in biomechanics. And the main thing I'd like to emphasize is that there's a difference between mechanical work and physiological work. In other words, the things that are happening outside of our body and inside of our body. If I take let's say a 100-pound dumbbell and it's on a rack, 100 pounds is kind of unrealistic for me. Let's say 50 pounds, and I take it off the rack and I lower it down to the ground. Then I lift it up, put it back on the rack, lower it, take it off the ground, and I do that 100 times. If I end where I started, then technically my mechanical work was zero, technically. But I'm going to be sore the next day. I'm going to be dying inside. My heart rate's going to be racing, right? So I have to be working, but technically the mechanical work is zero. And that's the key of the point I'm trying to make, is that physiological work is still energy, right? From our muscles, our adenosine trifosfatase, all that cellular stuff. There's movement happening there. There's one-way movement happening there. All right, processing, there's a machinery, there's a factory happening that's producing things while I'm doing this dumbbell example. And that's not to be discredited. So physiologically, my muscles are indeed working. They're doing a job, taking the dumbbell down, lifting the dumbbell up. How they work is going to be the concentric, eccentric, isometric. So you can have different types of work, but it's the physiological work that we're going to be mostly interested in, the stuff happening inside the muscle itself. So for our world, the energy is going to be happening in terms of adenosine triphosphates, elastic, stretchy energy that we can get from our tendons and the stretchy stuff like rubber band-like materials that create potential energy. That's what this is, potential energy. Power is just how much time did it take you to do the work. So remember how in the 40-yard dash, like when we add an element of time, we add an inference of speed. An inference, you run the 40, what was my time? 4.5 seconds. That infers how fast I was going. So think of power as the inference of speed work. How fast did you do the work? That's what power is. When you add the element of time, you add a speed component. That doesn't mean it has to be done fast. It just adds an element. So in other words, if you have two different people doing the dumbbell analogy, there's an element of work involved. But if they do the 100 reps in less time than me, they would have performed that exercise with more power. If it was the same dumbbell weight, but they did the work in less time, that would be an inference of power. In our world of clinical practical biomechanics, when you're in the real world with your athletes, with your patients, you're probably not going to be calculating numbers. That's for grad school. So my job is just to let you kind of know what's happening with what these terms are called and what they do. Okay? So I have some examples here. And again, we're going to infer, just to show you kind of how these things go. So on this page, we're doing a 40-yard dash time. Let's say player A is 200 pounds. And in the first sprint, they run it at 4.5 seconds. And in the second, they run a 4.5. the inference is, well, they did the same amount of work, the displacement, right? But they did it in less time. So the second rep would have been a more powerful repetition because they did the same work in less time. Kind of makes sense? And then you could, player B is the exact same weight as player A. So again, we can infer some things because they're the same. Once we get into different players that have different weights, well, then we have to kind of do some calculations. How much time relative to their weight? And so player C, just eyeballing it, would be more powerful because they're running similar times, but they are doing more work because they weigh more. You hear this a lot in sport where you have like a bigger running back who's running fast. And so they'll say like they're running with more power. You typically don't hear that for smaller running backs running fast, because smaller running backs kind of supposed to be fast. But when you have someone big moving fast, there's that inference of power. That makes sense? Like they're not actually calculating it and be like, this person is powerful because we worked out the math. It's just an inference of more work done in less time infers more power, more power. We talked about how powerlifting, and this is just one example, but powerlifting, power cleans, you're not actually measuring power itself, like doing the calculations, but there's an inference of time. To do some of these Olympic lifts, you have to move something heavy, that's the work inference, fast, that's the time inference. And so work over time is power. So there's the inference of power when you have heavy and fast. Speed and weight infers power. All right. What will you need to know for the trig stuff? I'm trying to set a precedent so that when we get into muscles aren't always just straight up and down. I wish they could all be like the bicep, but you have muscles that run at angles. And some of that pull, some of them run in 3 dimensions. Like on your test, you're going to have a muscle called the sternocleidomastoid. And it pulls in 3 dimensions of motion. So we have to look at things in terms of angles and components. So the muscle itself is just muscles only pull, right? But because it's at an angle, that means it can pull in a combination of directions. In layman's terms, like if I'm looking at my right sternocleidomastoid, it's trying to pull to the side and it's trying to pull forward. I'm going to explain all that why, but it's also trying to twist me. Okay. So our application of trig is to show you that the angle itself is not necessarily proportionate. It's squared, it's in proportion. A small change in an angle will actually lead to a significant change in component. A little change in angle from like 5 degrees to 15 degrees is a huge change in the components that make up that resultant, that overall pull or that overall throw. A small change in angle for release of a throw, like if you're working with a thrower, with a javelin thrower or a shot putter, small change in angles produce exponential changes in the components of the ups and the downs. That's what I'm trying to show you with the basic trig. So we have our cardinal directions, north, south, east, west, but there's infinitely many directions in here, but they're all made up of north, south, east, west. You have the ones that's in the middle, like at 45-degree angles, northwest. But if you go steeper, if you're more north, right? So like if you go past, let me use the northeast. you're at east, you're at 0. You're at north, you're at 90. If you're right in the middle, you're northeast, some of both, equal parts of both. If you're more north than northeast, then you say north, northeast. If you're more east than northeast, then you say east, east, northeast. That would be like saying 30, 45, 60, and 90. If the angle of whatever your resultant is less than 45 degrees, that means your x is greater than your y. So in other words, if I was at 30 degrees, without even doing the calculations, I know that I have to be more east than north, even though it's a combination of northeast. If I'm less than 45 degrees and I'm pulling with a muscle, that means that the muscle is pulling more across than it is up, but that doesn't mean that the upward pull is insignificant. Okay? So that's what I'm trying to get you to see with trigonometry. It's the constant blending of combinations. There's only, if you think about a 360-degree circle, right? There's technically more, but just if we round it up to the nearest degree, there's 360 degrees of options that something can be traveling in with a velocity, any vector velocity, or a force could be applied 360 degrees. I can pull this way, I can pull this way, I can pull this way, but there's 360 degrees rounding up to the nearest degree. There's only 4 options in those whole 360 degrees where all of the pull is exactly linear. In other words, not a combination. And that's only in 2 dimensions. This is a 2-dimensional picture. There's only, it could be east, where there's no combination. All of that pull, all of that throw is east, all of that throw is north, all of that throw is west, all of that throw is south, all of that pull is down, up, to the right, to the left. Does that kind of make sense that in the real world, there's going to be combinations because there's just more options to have a combination of any resultant versus everything is going up, everything is going down, everything is going, there's always going to be angles. Statistically speaking, there's always going to be angles. And so it's not that we have to sit there and calculate sine of x, it's just we have to understand that life deals itself in angles. And we have to be able to kind of see these combinations so that we can extract the up-down from the left-right. Up-down forces influence up-down motion. Left-right forces influence left-right forces. Y motion influenced by Y variables, X motion influenced by X variables. So when you have things in combinations, we have to be able to see what is X, what is Y, what is up, what is down. And the trigonometry helps us to do that. All right, let's see. I can never get, there we go. All right. So Cartesian plane, that's our X and Y. Most everything happens in a combination. This explains that. In mechanics, we talk about positives and negative spins, and that's to communicate exactly where something, like in other words, if someone says, I threw a ball at 75, at an angle of 75 degrees at a speed or velocity of 100 miles an hour, that's not going to happen for me, but well, 75 degrees from where, right? It's kind of like anatomical position for mechanics. We have to have a universal starting angle so that we kind of know where that ball is thrown or where that force is being applied. So that's what 0 degrees is. It's our anatomical position. Positive X is 0 degrees. And when we talk about angles, we start from our anatomical position, our 0. So 30 degrees from, 45 degrees from, 90 degrees from, 180 degrees from. the word we use for positive X or 0 degrees is from the horizon, which kind of makes sense, right? Like in our eyes, the horizon is pretty consistent. The across is pretty consistent because it's kind of perpendicular to gravity. So our angles are referenced to 0 degrees from the horizon, 90 degrees from, 180 from, 270 from, and then 360 from. So that's what this slide. And again, there's only 4 positions out of all of those different options where all of that force, all of that velocity, all of that speed is going to be all in the positive X, positive Y, or negative Y. Meaning that a majority of the time, there's going to be combinations of stuff. We subclassify things into quadrants. That's what Descartes did. So quadrant 1 is basically any angle that's between 0 and 90. So if I was going to throw a ball and I say I throw it at 70 miles an hour at an angle of 30 degrees from the horizon, I know that it's northeast, right? I know that the X component is going to be east and the Y component is going to be north. Positive, positive. If I drift off into quadrant 2, that's going to be between 90 and 180. The Y is going to still be positive. In other words, it's going to be going up, but now the X component is going to be to the left. It's going to be a Y component and a negative X, a positive Y and a negative X. If I drift off into quadrant 3, meaning I'm throwing a ball or I'm applying a force somewhere between 180 and 270, that's down and to your left as we're watching it. Well, all that's telling me is that the Y component is going to be negative and the X component is going to be negative, negative, negative. And if I apply any resultant velocity or force in between 270 and 360, the Y is going to be negative and the X is going to be positive. Pretty straightforward. Just we're replacing north, south, east, and west with positive Y, negative Y, positive X, negative X. North is positive Y, south is negative Y. East is positive X, west is negative X. That's all we're doing. So it's just a cardinal system, but instead of north, south, east, west, it's positive Y, positive X, negative X. And instead of saying northeast, we have a resultant. And you just have to know, oh, okay, that's going northeast. That's positive X, positive Y. And if I'm steeper than 45, I'm sorry, if I'm between 0 and 45 or less than 45, then I know I have to have more positive X than Y. That's east, northeast. And if I'm greater than 45, in between 45 and 90, it's going to be north, northeast. I'm going to have more Y component than X. So 45 is going to be equal parts X and Y, equal parts north and east. And if I'm shallower, if I'm closer to X, then it's going to be east, northeast. Like I'm going to have more X than Y. And if I'm steeper, I'm going to have more Y than X. It should be kind of common sense. But that's important because we're going to have some muscles that are very steep. We're going to have some muscles that are very shallow. And those shallow muscles still have a northern pull. And it's more than you think because of trigonometry being squared. So you may see a muscle that has a very steep angle. And I may say, hey, that muscle has a Y component to its pull. It's pulling up. And that may be kind of hard for, wait, what do you mean it's pulling up? Look how shallow that pull is. Yeah, but it still has a component of Y. And that component of Y, although like linearly it may seem small, because of trigonometry, because it's squared, it's actually greater than what we realize. All right. This stuff is should be pretty reviewable, right? This is just when we're talking about vectors, scalars, vectors. It has to have a magnitude, a direction, and the direction is the northeast, the northwest, the southeast, the southwest, positive X, positive Y in quadrant 1, positive Y, negative X, quadrant 2, negative X, negative Y, quadrant 3, negative X, negative Y, positive X in quadrant 4. So that's what direction means. The angle relative from the horizon or from positive 0, 30, 45, 60, 90, da, 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 okay? I'm going to use, like when we're looking at muscles, I'm going to use like arrows to show you angles of pull. We call it angles of inclination, but just angles of pull. And so that's what kind of that means. Hey, look at how that muscle is pulling down and across. And look how that, like an oblique, for example, like our left external oblique has a pull that's down, and it has a pull that's across, and it has a pull that's down laterally, forward, and revert and transverse. So eventually we're going to get again into 3 different dimensions. Trigonometry allows us to kind of see 2 dimensions, and then eventually we'll work towards that 3rd dimension because I'm going to give you a different view. One of the limitations of a 2-dimensional picture is that it doesn't give us a 3-dimensional picture. So my job is to give you a different view so that you can see that 3rd dimension. Meaning, if we're going to look at the right sternocleidomastoid from a front view, it may be easy for you to see how it's trying to pull the right ear to the right shoulder. Okay? But a side view may make it easy for you to see how it's trying to pull the chin to the chest. And then a top view may make it easy to see how it's trying to pull your right ear forward, not literally, but just close enough, and it's trying to make you want to look to the left. So my job is to give you different views so that we can still apply the same concepts. But 3-dimensional concepts are hard to see with limited views. That's what I'm trying to say. All right. For your test, all I'm asking you to do is know definitions. Okay. No, I'm sorry, I saw a comment, and so I was trying to catch up with that, but I think it's a bot. So on the test, you guys, just basic definitions. Know the difference between collinear and concurrent. I know they sound alike. Collinear vectors is when multiple forces or vectors are lined up when we can compare apples to apples and oranges to oranges, meaning they're in the same direction. I'm running with a backwind, so the wind is going to help me run forward. I'm running into a headwind, so the wind is going to, the wind is in the same direction as me running, so it's going to affect me. X force is X motion, Y force is Y motion, that's what that means. Concurrent forces, this is the weird one. It's where different forces are happening in the exact same place, but in different directions. This is like when you jump from the ground, like doing a standing long jump or a standing broad jump. The push from the ground is at an angle. So in other words, if I had a force plate and I jumped and I measured that push that I feel from the ground, it'd be at an angle. The Y component of that push is making me want to go up. And the X component of that push is making me want to go across. That's the friction. But they're happening in the same place. They're happening at the same point, but they serve 2 masters, if that makes any kind of sense. Meaning that if I didn't supply an X force, I wouldn't try to go across. So concurrent are 2 perpendicular forces that combine to form one resultant force. And they're happening in the same point. They're happening at the same place. But because they are in 2 different directions, We can't like add them together to mean anything. I can't say the X is this and the Y is that. So when we add it together, it means something else. X force is X motion, Y force is Y motion. If all of my energy is going straight up and there's nothing that's propelling me across, I'm not going to go across. Only the X force can make me move across, and only the Y force can make me go up. Okay?
Yeah, that's a bot.
So just know the basic definitions of these two for the test. I'm not going to ask you to solve. I'm not going to ask you. I'm just going to ask you to know the difference between collinear happening in the same direction. We can add, subtract. We can do math with that. We can balance our checkbook with that. Concurrent is like an X and a Y happening in the same point, in the same place. But because one is a Y and one is an X, I can't compare apples and oranges. I have to look at them separately, even though they are part of the same resultant. That resultant, let's say my pin is the arrow, some of that force is Y, and some of that force is X. And only the X can affect X motion, only the Y can affect Y motion. Same thing with muscles. When we're looking at the components of muscles pull, let's say like upper pec, only the part of the pec that has upward pull can influence my shoulder in an upward direction. Any component that's just across isn't going to try to make my arm go up. So in class, I talked about components. This would be a good example of concurrency. You have a muscle that's F pulling at one point. And at that one point, I have a parallel component that's trying to create stability, and I have a perpendicular component that's trying to create mobility. But both of those things are happening simultaneously in the same place. That's weird. I get it. But again, if I throw a ball and it leaves my hand with a velocity of 70 miles an hour, it's not hard for me or to think we can visualize that that motion is happening in the same place, but some of that motion is here and some of that motion is there. That's what concurrency is. Here are some examples. So again, when we get into muscles, most of our muscles are going to be pulling at angles, and it's my job to show you the different components, the different jobs those muscles are doing. A sport analogy, kickers only kick. 3-point shooters typically only shoot threes. Our muscles have to be more versatile than that. We have to get more bang for our buck. We have to get more efficiency with our muscles. So most of the time when we talk about muscles, we're only talking about the fun stuff, the movement stuff. But muscles also are big players in joint stability. They're doing other jobs besides just movement. Protection, maintaining our joint stability, our joint integrity. And so sometimes these muscles that look very linear have angles that are serving different jobs. And sometimes muscles that are at angles are serving multiple movement jobs. They're pulling in multiple directions of motion and also pulling in stability as well. So as you can see, it could get kind of confusing with all these different jobs. That's why I'm just trying to show you that because muscles pull at angles, the different components of those angles, the concurrency, serve different tasks. Dr. George used to say, give unto Caesar what is Caesar's. The X pull might serve a different function than the Y pull. Stability, translation, trying to draw that bone into the other bone. Mobility, creation of moment, torque, rotational influence, preventing, causing, or allowing motion. Here's another example of exactly what we're talking about. This would be like the deltoid, which all of you are familiar with. That muscle's pulling at an angle. There's concurrency there. The X component in this case is trying to translate that bone into the socket to prevent dislocation, and the rotary component. So using in layman's terms, this resultant would be like northwest pull, positive Y, negative X, up and across. The across is literally the muscle trying to maintain stability. And the Y in this example is the muscle trying to create rotational influence. So in other words, not all of that muscle's pull is trying to rotate you. That's what I'm trying to get you guys to see. All right, that's what we're gonna stop with today. Hopefully everybody's caught up. Again, no new material, just trying to reflect on the importance of basic concepts. How would I ask questions? We're not gonna solve for X, but I'm trying to get you to see how these different variables affect each other. And that'll make you better clinicians down the road, okay? I hope everybody's staying safe, and we'll see you Friday.